Okay, thank you. That was a very nice welcome introduction. Welcome from you. Thank you, Kate, for inviting me today. Thank you for all the technicians and everybody here who is making this thing possible, to the volunteers that so excitingly provide this program for you. I took a peek a little bit in what you were doing here. Sounds really cool. I like the maze. Did you like it? Okay. Didn't you do the maze? And the pinkberry, the raspberry? Where was that? Raspberry? Okay. So a little bit about myself. I was asked by Kate to provide, a short message to you. I really believe that perseverance, curiosity, honesty, and hard work always pays off, always. And in general, and this is maybe a little bit hard to grasp, when you feel that you need to decide something, whether it's something little or something big, it's good to try to make that decision with both your heart and your mind. So that's why I said try to have a clear mind and a kind heart, because those decisions will always drive you to the right path for you in this life. So a little bit about myself, and I call it expanding a bubble. I come from communist Romania, and I end up working here at the space portal, NASA Ames, Silicon Valley. And I very much believe that we humans are a very interesting synergy of emotions and logic. And so I try to tune my story today to you to hopefully inspire you not only on the logical, technical side, but also imagination. In the end, Albert Einstein, and this is one of my favorite quotes, said, imagination is more powerful than knowledge. You can know everything you want in this world, but if you can't tie that to your imagination, and again, to your heart, you only take so far. That will only take you so far. So my motivation, by the way, I've never wanted to work at NASA. Never crossed my mind. Where I grew up, I never even heard of it. So my motivation was always curiosity. Where do we come from? What is this universe about? What brought us here? Where will we go after this life? And these are really, really deep philosophical questions that at some point in our lives, we have to sit down and ponder. And the earlier you do it and the more frequent you do it, the more you're going to find your own answer and your own comfort with them, because nobody has the final answer. But you see, look at this picture. And funny enough, at that time, it was just my imagination of how the universe looks. And this is, in the upper right corner, that's the Hubble telescope. It's a telescope on Earth's orbit. And it took an image of the darkest sector of the sky, a 24th of the whole sky. It was dark, right? So from Earth, if you look into that corner of the sector of the sky, you see nothing. And that's the picture that came back. So that density of galaxies and solar systems makes me think that we're so tiny. It's like a pixel on a really, really big image, right? And so how can we, with just this little tiny experience of our life, still make a meaningful contribution to this huge, vast universe? And I'm really, really sure we're not alone in here, but who else is out there and in what form, we have no clue. And so whenever you feel like, what's my role in this world, think about the millions and millions of questions that are out there and that each of you individually can pursue in a meaningful manner. So going back to that black hole, the bubble I come from is Romania. And it was meant for me to come in the US. I thought about it later in the life because I'm born on the 4th of July. So that's funny, right? By the way, do you know where Romania is? Europe, right? Yeah, it's in Eastern Europe, and the Eastern Bloc has been under communism for several decades in the past. The funny thing is, when I turned 14, a friend of my dad was a journalist, and early in my life, I never thought about science and technology. I was just, I like literature and journal. I was convinced I was going to become a journalist, actually. And so my father had a visit from a former friend who moved to the United States, and he brought him a copy of the Declaration of Independence. To me, that was like a little piece of unimaginable information from a country that I could barely grasp the idea of. And so I held it very dear to my heart for many, many years, and it actually helped me shape the certain beliefs and ethics that I do hold very high. So I encourage you to get a copy of it and try to read it and see what you understand, what you don't, and what you don't, why you don't understand. So this is funny. This is communist Romania. It started with actually a good idea, but it was really implemented very, very wrong and incorrectly. And it became a really like a showcase of ego and personality. So we had old buildings where our president's image was all over. We had his image in our classrooms. Every morning we had to say our commitment to the country and so on. And then funny thing about on the left, so our president one time hosted the president of France, de Gaulle. And when they took the photo, they realized, he's so much shorter than the French guy. So they asked the newspaper to edit that image out and put a hat on his head so that he looks taller. Now, what they forgot is that he was actually holding the hat in his other hand. So the newspaper came out with that image, and in a panic, last minute, they put out to recall all those newspapers back from the entire country, try to really keep control of those. Of course, people saved copies, those who had them. The guy lost his job and so on. But just an example, on how, trying to fake things will never take you too far in life. And so at that time, I used to be part of these massive demonstrations. We had hundreds of hours of training to coordinate and make sure that we have the right color and so on. We would get no water, it would be hot. It was pretty hard to be in those things, and I never understood what was the purpose for it, but I had to do it. And so the only thing that connected me to him, to this big celebration that was August 23, and that was actually the national celebration for Romania at that time, because that's when Romania signed a treaty with the United Nations against the Axis, the Nazi Axis. My grandfather, and you can see the many decorations, he was a World War II veteran. He actually worked in the front lines. I mean, he went in the front lines, and he basically walked the first line from Romania to Czechoslovakia and back. So that was a couple of months fighting against the Nazis. So to me, the favorable or the positive side of this event was that veterans like him, the war really played a huge impact in his life and indirectly on our family life, were still honored at this event, and I think that's what kept me through all those long hours of training. So this is how I looked when I was your age. That's the right side picture, and this is when I was early. So I was a communist scout. We had to be. You had no choice. You had to be enrolled in these things. So you see, it was very uniform. You didn't really have to grow any individuality, right? It's really a very uniform thing. The other thing I want you to notice, okay, there you go. See a big difference? Here, you have cell phones. You have technology. You already are in love with science and technology, right? It's part of your daily lives. I've never had a cell phone until past 2000. The first time I touched a computer, which was a really, really very old version of a computer, was when I went to university. So I was 18 years old, 19 years old when I saw the first computer. So that was, and I don't think I regret that. I think I caught up with it. I really love, though, the pastoral side of Romania, and I still very much keep the connection with nature. It helps me recenter, it helps me recalibrate, and I also spent my summers at my dad's, my grandparents from my dad's side. They had a farm, and I worked the land. I planted seeds, I watered, and then when we had to cook, we had to go in the garden, and well, what can we cook today? Well, we only have this and this, so then we're gonna cook what we have, right? Pretty much, it teaches you how difficult it is to be self-sustainable and to also understand how hard sometimes you work for things that maybe don't taste as well, but it's fun. And you also get to enjoy more because you know it's the fruit of your own work. So here's my trajectory, like I said, from Romania. Then I went to Western Europe, and I ended up to the United States. And as a woman, I very often felt that I didn't have a voice in a room. That when I had a brilliant idea, someone else said, like to that lady, "Oh, that's an excellent suggestion, Ms. Triggs. Perhaps one of the men here would like to make it." So what I thought is, I really have to work hard and build education, because if I have education and if I build confidence to that education, then I will have a voice. Of course, along the way, I've had different mentors that I hold really dear to my heart, and they were inspiring and always believed in me, so I'm really grateful to them. But at the same time, I also had role models maybe from outside of this world, right? Like a lot of women astronauts, for example, who can do amazing, difficult things in space. And I thought if they could do those things, I could go through the hardships of life too. So a couple of things. I think while I've started more on the science side, and during my PhD, I have a PhD in physics, I worked more on porous media and trying to model flow, and you can see here some molecular species going through the porous media and so on. So these are models that rely a lot on analytical skills, right? Solving mathematical equation. That's why you learn math in school. Analyzing data, doing experiments. That's why you learn in school to do lab experiments, right? Design your own experiment. Make sure that your data from your experiment to your calculations matches and so on. I really believe that the best answer is always a combination of experiments and simulations. So, and then from here, when I moved to the United States, I went to California Institute of Technology because I was interested in understanding how do atoms form these materials. And so I learned computational chemistry, and I used a software where it allowed me to pick atoms and build a structure such as this, and then play around with the structure. Through that structure, it's what we call these days material design. So we design a structure, and then we study its properties, or vice versa. We tuned the inside of a structure in order to accomplish certain properties. Another project I worked on is, sorry, I should go back, is a DNA, designing a nanopore. So that's a really, really tiny pore, 10 to minus 9 meter in diameter, where we drag the DNA through it, and we wanted to sequence the DNA. So that's what we called a DNA sequencer, a nanopore sequencer for DNA. And so that technology actually has progressed tremendously over the past 10 years. These are a couple of things I worked on the scientific side, but then, once I moved, so by the way, the DNA, I mostly worked on it at Stanford, and then from Stanford I moved to NASA. And NASA, it's a big pool of engineers, so of course I was curious to learn about the engineering side, and I worked on Stardust and Mars Science Laboratory, specifically more on the entry, re-entry aspects of it. So you can see there's a lot of science, again, science, engineering, and technology that's needed there. The image to the left is basically a map of the heating that you see on the thermal protection system. There's a huge heat shield that protected the Mars Science Laboratory mission upon entry in the Martian atmosphere. So we did a lot of simulations, and we had plugs on that heat shield to do the measurements so that we can actually calibrate our models according to which we do the design. Remember the experimental and the theoretical side? So really, these were data from a different world, from entering into Mars, that we were trying to calibrate our own models against. So that's very, very cool. It's a little piece contributing to that mission. So what I do now is I realize that there's a lot of scientifically cool ideas, a lot of engineering things. However, we have a pool of solutions and a pool of problems, and 95% actually of the solutions don't make it to address the problems, because beside the technical side, you have the market, the business, and the funding that need to align. So what I do very much these days is I try to keep in mind that I'd like to see more of this solution-problem connection happening out there, and specifically related to new space. So what's the new space? You've all heard of SpaceX, okay? Blue Origin, Jeff Bezos' company, right? Bigelow Aerospace. Okay, so these are private sector investments into developing capabilities that we can go to space. So let's watch a short movie on that.
T-minus 1 minute, vehicles will start up.
Final go, no-go poll for launch. All stations respond when polled.
Sys1 is go.
CC1 is go. Flight software is go.
Nav1 is go.
And MBs go.
3, 2, 1. And liftoff of the Falcon 9 rocket and Dragon.
Falcon 9 clear to go.
SpaceX continues America's mission to resupply the International Space Station.
Vehicle supersonic.
Stage separation confirmed.
Impact ignition confirmed.
All stations, MB Mission A, successful Dragon F9 sub. Thank you for the ride, F9.
You are go for the capture system.
And capture is confirmed.
Dragon is restoring America's capability to deliver and return significant amounts of cargo to and from the space station.
There goes Dragon away from the arm.
Confirm visual on splashdown.
Okay, so a lot of IT, a lot of robotics, a lot of autonomy, a lot of technologies building these different pieces of hardware, right? So right now, what we have in Earth's orbit, and it's permanently inhabited since 2011, is the International Space Station. And just to give you an anchor point, it's more than 100 years ago that humanity ever dreamed of having an outpost. So at that time, that was science fiction. Right now, it's reality. So we can turn science fiction into reality, right? It just takes some time and some effort, but we see a lot of acceleration lately. And so the other interesting thing in space is whether you're in Earth orbit or some other place outside of a surface of a planet, you're going to have a reduction in the force of gravity. So things are going to float. And so what we do a lot on the International Space Station is we study how systems from life science systems, little bacteria and viruses, up to the scale of a human body, how do they behave and potentially adapt to a change in gravity, as well as material science systems. So here on Earth, everything segregates. In space, they stay in a uniform distribution, right? That's why you have water in a spherical form floating through a room, which here wouldn't happen, right? And all this is a huge engine for innovation. How do we tap into that? And so that is currently the struggle. And the new space move, like I said, it's really pushing this envelope forward quite aggressively. So one thing we do, what can we do there? We can make exotic optical fibers, right? Like right now, telecommunications, internet, all rely on silica fibers made in gravity. Gravity is a hampering force, actually, in the quality of these fibers. And these fibers are going to be supporting the next generation of needs that we have on ground. We can do, so miniaturization in space. There's an electronic nose that was developed and miniaturized to be used on the International Space Station to follow different chemical volatiles or bacteria. Because of that miniaturization, once it was brought back on Earth, it spun off a myriad of applications, including what you see on the bottom left corner, the ability to try to predict cancer early on. The next thing is we can make things in microgravity, manufacture things in microgravity with improved performance. This is called ice templating, and it's because you use the water first to form a matrix, and then you populate that. So you control the microstructure and you control the properties. So these are just a couple of snapshots. Something else that we can do in space is, so we talked about this reduced gravity, right? We also have infinite solar power. We have the cold of space. We have the vacuum of space. So there's a lot of resources. Plus, there's asteroids, there's moon, and there's a lot of raw materials that could be extracted that we could never have access to such quantities on Earth. So technologically, those things are there. One application, for example, of solar power and cold is solar power data centers. Imagine moving the data centers into space. And there are actually companies who are really looking into how they close the business case on such applications. As I mentioned, Planetary Resources is looking into how do you take an asteroid, mine the asteroid, bring those raw resources back on Earth, or use them in space. So is Deep Space Industries. These are other companies, again, that are looking in how do we take and leverage space resources for the benefit of Earth and also close the economical case. So we're working in building that infrastructure, expanding beyond the International Space Station, expanding beyond the Earth's surface to include Earth orbit in our daily lives, and again, leverage upon those resources. So here we are at the tipping point, at a confluence between, on one side, Earth challenges and the opportunities that we can really use and leverage from space. And so I think where we are right now is we're thinking, how do we best do that? How do we best leverage that? And you guys are gonna do it. You're gonna pick this up and you're gonna scale it up and hopefully make the greatest things out of it. So imagine that the Earth space confluence, right? Look at planet Earth and look at an asteroid in space. They both float in space. They both need to survive, and they need functional ecosystems in order to not disappear. So when you think about yourself and your needs, think that the planet has the same needs, and how can you, remember, use that kind heart to connect to that? So whatever technology you decide to develop, can you make sure that long-term that technology would serve both you, the people who you think are be using it, but at the same time is kind to this planet? So, because again, we see a lot of pollution, we see a lot of degradation in a lot of these ecosystem services, and actually the United Nations did a global assessment in 2005, and out of the 24 ecosystem services, only 4 are unchanged. All the others are under severe degradation, and that should be something of really serious concern to us as a species. We're working right now, actually, one example I'm going to give you in developing an idea on one of the Sustainable Development Goals that the United Nations has put out, and it covers so many different areas. But for example, on the climate action, connecting this Earth-space confluence is how about moving polluting manufacturing off the surface of the planet into space. And Jeff Bezos actually has that motivation and has expressed it before. So each of us has an integrated circuit in our phones. And the production in 2015 was 900 billion units. Each unit has about 1 million or 2 million of transistors, depending if it's Apple or not. And so in order to make one integrated circuit in average, you use about 2,200 gallons of water, out of which 1,500 has to be highly purified water. Those are non-renewable resources that we never send them back in a pristine form. In space, we actually, in the 1995 era, with the space shuttle, NASA deployed behind the space shuttle in the wake a 4-foot diameter shield. And in the wake of that shield, it used the cold of space, it generated ultra-high vacuum, and it used the oxygen from space to print wafers. We can do it. We just need to scale it up and look at the details of it. And so I want to leave you with one thought here. Whether it's technology, whether it is imagination, it's ultimately about ethics. And what is the ethics that you develop for yourself in life, and can you stick to that and hold it to high standards? Because you see, if we forget about these things, we end up into pretty big problems. So please remember about that. And whenever you feel sad or disappointed or down, take a moment, sit down, look at the sky, and remember who you are in this universe. Thank you.
All right, thank you so much. And I'm sure some of us have some questions, and we have another few minutes to ask some questions. So any questions right away from anyone? Paul has a microphone over there, and I have one over here. What do you think? What resources could outer space provide away from our planet? Light?
Well, so there's asteroids who are ice asteroids, for example. And the reason that's important is, again, that's a source of water. But we also know that in order to use transportation or develop transportation in space, what we need there for propulsion is water. So you could have basically the equivalent of petroleum in space, which would be water mined from these asteroids. There are huge asteroids that are formed completely out of platinum. If you take all the estimates for platinum right now on ground, on Earth, what we could ever mine, it's a really small fraction of all that. There's titanium, there's aluminum, there's a lot of elements out there. Because again, all these elements actually formed in the Big Bang. And they were distributed along all these, around to all these planetary systems, solar systems that are out there. And so again, it's just a matter of forming that matter and accessing it in a meaningful way.
All right, questions?
I feel like I failed if you don't ask me questions.
How many of you have ever
Yes, there's a
considered
question.
doing that kind of work? Anyone? Oh, we have a question back here.
Why did you join NASA?
Again, it was, at that time, I was working at Stanford on the nanopore sensor, developing the nanopore sensor. And that was a collaboration with the NASA Ames Center for Nanotechnology. And it was more that side of things that drove me there. Again, I never set my mind that I want to work for NASA. So it was sort of like a serendipitous thing that happened for me. Yeah. Come on.
Any questions on the other side of the room? Oh, there's one over there.
For you, what was the hardest thing about transitioning from like being politically interested and active to a career in technology?
Can you repeat that?
What was the hardest thing about transitioning from being, focused on political activism to technology?
Well, okay, so you mean being a communist scout?
Yes.
Yeah, okay, so I had no choice. We all were communist scouts at different levels, right? And in 1989, actually, Romania underwent a revolution, and so the communist regime was removed, and so all of us automatically lost that, and I was honestly never interested in becoming one anyhow, if it would have been by choice. The other thing is growing up in that bubble, because again, communication outside of the border with Romania was very, very restricted. Actually, I read a lot of books about North Korea, very similar, right? And I read a lot of personalized histories of people who lived there and, took the risk to run away to really, fight for freedom and find freedom. And so I felt the same way when that revolution came and the bubble burst. I felt like I want to go explore the world. I want to understand this world. So I think it was more that side rather than political activism versus science. So yeah, but yeah, thanks for the question. Yeah.
So I have 2 questions. So for the Voyager missions, for deep space missions, what do you use for fuel? Like, how do they run for such a long amount of time?
So the Voyager used what we call a low radioactive source to power itself.
Okay. And also, for Saturn, there's like a mission that's there's a mission for Saturn, and it's running low on fuel, and it's gonna go around its rings 22 times or something, and then crash into it, right? So will it actually be able to pick up when it actually crashes into the planet? Will it be able to pick up anything? Will you be able to find images or stuff from that?
So, okay, so that's a good question. So we do a lot of the missions. I don't know exactly which particular mission you refer to. There's many, many missions at NASA, but I'll give you a more generic answer. So there's a lot of robotic missions. Some of them are observational, which means they're from the orbit. Most of them, actually. You send a spacecraft, it will orbit the planet or the body that you want to observe, and it will actually send back a lot of images and information. Then the next level is, do you want to now, that mission go through the atmosphere, go to the surface? These are, next level, next generation of missions. So like Mars, for example, yes, we have a lot of rovers, right? So we got the opportunity to study during entering that atmosphere, what kind of elements you have there. One thing that we don't have, though, is a return mission, right? So you want to actually get something from the surface and bring it back on Earth. And so there's people who have been designing this kind of mission. It doesn't happen because we have very strict, what we call planetary protection rules. And whether they make sense or not, that's a different story. But we want to make sure that we're not bringing something deliberately from a different planet that could harbor a small microorganism that could exterminate human race. So there's a lot of caution there. On the other hand, you could say, well, we have all these asteroids or meteorites that are constantly colliding into our atmosphere, burning into the atmosphere and hitting Earth's surface. So there's scientists, there's a whole pool of scientists who are looking into our planetary protection rules and the rules of if we go to a different planet, how do we make sure that we don't leave damaging footprints on a different planet? So.
All right, we've got another question over here.
My question is, as a young person interested in technology, what would you recommend what are some things you would recommend getting involved in, or some things yourself when you're early parts of starting getting interested in what you're interested in?
Yeah, so of course, the way I see things now are very different than the way I saw things 20 years ago, right? And this is what I tell my kids too, go have an internship in a startup, go have an internship in a government organization, but go also work at a farm or go work at the place, right? It's that solution problem thing, right? You get enthusiastic about building a solution, building a piece of code. Why, right? Is it just that you have fun? That's fine. If you're really hoping to develop a technology that will solve something, go and try to learn something about the environment that you think that solution is going to be useful, and try to see, wait a second, am I realistic here, right? What are the day-to-day challenges that I need to make sure that the technology will be customized then for? So, make sense? Okay. Yeah.
So you mentioned Mars earlier. I think I'm not the only one wondering, how long will it be until we can actually colonize it? Or even get someone to live on there?
Yeah. Well, okay, so that's why I did that exercise with the International Space Station, right? So it was 150 years from the first time that we know someone had an idea of building an outpost from the surface of the Earth, right? Where we are now with Mars is we've sent several robotic missions. We haven't sent a human there. This is actually Elon's hope. That's what he wants. He wants to colonize Mars and send hundreds of people there. And we don't know. We don't know if we can survive. We don't know how we're going to, I mean, we have plans, we have studies. We haven't really built one habitat so far, right? So if you think of the whole infrastructure end-to-end needed from where we are now, right? When are we going to build the first outpost? How is that going to look? From that outpost, how do you scale it up, right? I think we're at least 50 years away, if not more, realistically speaking. But I may always be wrong. So, yeah.
How far have you gone? Like, what atmosphere and all that have you gone? Like, what planets?
Can you say that again? I didn't hear you.
How many planets have you found so far?
Have I what?
How many planets have you found?
How many? Oh, how many planets? Oh, I see. Okay, so that's a good question. There's it goes down. I'll take a little detour here. There was a gentleman called Francis Drake, and his question was, what is the probability of finding intelligent life such as ours somewhere else, right? So humans or more advanced, right? And so he thought about it and he said, okay, he came up with an equation, and that equation is a multiplication of probabilities. And it starts with what's the probability of having a solar system the size of our solar system with one star and several planets? What's the probability in that solar system to find a planet in a habitable zone such as Earth is here, right, with reference to sun? What's the probability of that planet to have been around for as long as Earth has been around? So Earth has been around 4 billion plus, right? Because you can have a young planet that doesn't leave enough room to develop, life. So one probability in that equation is how many Earth-like planets are out there, right? And so Hubble, and then there's another mission, Kepler, both spun out of here from Ames. They are looking exactly into trying to see, can we find Earth-like planets out there, right? And so, as you've seen recently, apparently we've increased the number to about 7, right? But that's because we're really looking into one particular spot out of the millions that are out there, right? Now, what does that mean in terms of life? It's really still a far answer, because life can be in two forms. Can be just biological life, which means you can find a little bacteria or microorganism, or it can be intelligent life. So I can expand on that more, but I hope I answered your question.
All right, we have time for just 2 more quick questions. So one over there.
I heard that there was a planet that, that's exactly like ours. I think it's Kepler 22b or something. How many light years does it take to get here? Like, how many years does it take?
Can you speak a little bit louder and more clear? Because I can't understand what you're saying. Thank you.
I heard there's a planet that's exactly like ours, like Kepler 22b, I think. Do you know how many years it would take to get there?
So how many years it would take to get where?
To Kepler 22b, I think.
To Kepler?
Yeah, it's a planet that looks exactly like Earth, and it's like habitable.
So if we were to travel, let me see if I understand it right. If we were to travel on one of these planets, how long it would take? That the Kepler mission discovered. So Kepler is a mission, right? These planets are usually, so when we travel in space, we don't use miles, we use light years. And so that's a really long time. And right now, it would take several tens or hundreds of those light years to get to any of those planets for a human. Also for a robotics mission. So we actually do not really have the technologies to accelerate us, to move us fast enough so that we can also, we're also alive by the time we get there, right? Very interesting, so there's a competition that Elon Musk just hosted last week, the Hyperloop competition. And so that is one step towards developing that capability. So check it out.
All right, one more question here.
I heard that NASA found those 7 new planets, like 39 light years away. How long will it be until we can colonize those?
That's a good question. I think if you're lucky, you may see some of those, but I really think it's 2 generations or 3 generations away.
All right, and we have one last question over here.
Hi, what you're working on now, of all of those, if you could pick one that you're most excited about that will impact the Earth in a positive way in the future?
Yep. So, I don't know, there's so many. I would hate to call a favorite, right? But I think the one that I'm, and again, I'm trying to create more the environment for all these ideas to grow. But this idea that space technology, so like I said last, this technology ethics, and that lately we see the negative long-term effects of using a technology and the impact on the environment and so on. And so the idea there is most of the time these technologies are funded in order to, or optimized in order to provide a return on investment on a short term, right? If you look at these plans of colonizing planets, it boils down to understanding how can you live sustainably. So all the space technologies that we've developed that are used on the International Space Station, and by the way, I encourage you to visit AIM's sustainability base, which uses some of these technologies back into the built environment. All these technologies are not optimized for a return on investment. They're optimized for how can you ensure in a very unfriendly environment long survivability. So I think several of those technologies would be very, very beneficial to align with a lot of the problems we see right now, and one of the mechanisms is through the Sustainable Development Goals. And so just increasing the awareness of that fact, and how can we now connect the pool of space technologies with global problems of sustainability. So I think that's, in a nutshell, I would say, I find it really inspiring and important.
Great, thank you. So we are going to wrap up. Do you have any last kind of words of advice or anything to kind of help all these amazing students in the room think about how they can move forward with some of these great opportunities?
Yeah, travel the world. Learn what this life is about beyond technology. Again, try to balance out technology with other things. Like music, or writing. Develop yourself in your entirety. Don't let just one side drive you. But that doesn't mean not to follow that path. And again, be kind to yourself and to human race.
Excellent. Thank you so much for joining us today.
Thank you. Thank you.